welding any type of joint, and in whatever position it may be, magnetic disturbance of the arc, more commonly known as arc blow, is present to some extent. When this disturbance is excessive, it becomes very difficult to control the molten pool to produce good uniform welds. The operator is forced to fight arc blow, and the work usually suffers in quality. When direct current is used for welding, arc blow is likely to become excessive on work involving corners, and it is particularly troublesome at the beginning and end of joints. However, this obstacle to good welding can be eliminated. The purpose of this picture is to show what arc blow is, how it interferes with production in arc welding, and how its effect is counteracted by the use of alternating current. With alternating current, or AC, the current flows through the electrode, the arc, and the work, first in one direction and then in the other direction. The basic difference between the AC arc and the DC arc is this reversal of current. It has a very definite effect on magnetic arc blow. But first, let's get an idea of what these magnetic disturbances are and how they affect the arc. In order to demonstrate this, let's suspend a copper wire so that a magnetic field can be brought to bear on it. As long as no current is flowing in the wire, the magnet will have no effect. But if direct current is passed through the wire, it will be attracted or repelled depending on the direction of current flow and the polarity of the magnet. The same thing will happen if a magnet is placed near a DC arc. The arc will be deflected the same way the wire was, and for the same reason. When welding with DC, the current flowing through the arc and the work causes a magnetic field to be set up in the work. This magnetic field affects the arc exactly as if a magnet were placed near it, deflecting it from its true course. And as this becomes excessive, the arc gets to be erratic and hard to control. This makes it possible for old man arc blow to say to the operator, "Phooey." And there's not much the operator can do about it. As we have already seen, when AC is used, the current changes its direction, flowing first in one direction and then in the other. The magnetic field set up in the work by this alternating current, naturally, every time the current changes direction. As this magnetism builds up and dies down, circulating currents of electricity are caused to flow in the work. These circulating currents, in turn, produce magnetism that opposes the magnetism produced by the welding current. The effect on the arc is canceled out, and now the arc is stable and does not deflect. Good, stable welding conditions result. And now the operator can say to old man arc blow, "Phooey on you." Power for alternating current arc welding is usually supplied by a welding transformer. In a widely used AC welder, a crank at the top of the unit regulates the welding current. Turning the crank changes the spacing between the coils and raises or lowers the welding current by changing the magnetic effect of one coil on the other. A current indicator on the side of the case shows the approximate current which will flow when the arc is working. The smooth, stepless control afforded by the crank permits easy adjustment for minor changes in welding current that may be caused by variations in the length and arrangement of the welding leads or by a change from one type of electrode to another. This type of welder has ample overtravel beyond the rated current setting to provide full rated current output, even when welding with leads as long as 200 feet or more, and for any ordinary arrangement of these leads. The technique of welding with alternating current is practically the same as with direct current, and the four main factors fundamental to all successful arc welding still apply. In AC welding, the current settings can often be higher than those used with DC. It is important, however, that these settings be correct for best results. When the correct current is used, and the other factors are also correct, the molten metal flows evenly to the rear of the pool, forming a smooth, uniform bead. Too low a current makes the bead high and narrow with poor fusion, while too high a current results in a wide, unruly molten pool with excessive spatter. The second factor, travel speed, must be suited to the thickness of the work and to the current setting and size and type of electrode. If travel is too slow, the molten metal piles up and there is danger of burning through the work. With too fast a travel, fusion is poor and the weld is narrow and irregular. The third main factor is the length of arc. Too short an arc is hard to maintain, and the weld is likely to trap slag and gases. If the arc is too long, it is erratic and spatter is excessive. And now, the fourth factor, angle of electrode. It is in this respect that AC welding contributes the most in simplifying welding technique. In welding with direct current, it is often necessary to manipulate the electrode in an effort to overcome the effect of arc blow. When arc blow is severe, as when welding in a corner, the resulting weld is irregular. Spatter and undercutting are excessive. A cross-section shows poor fusion and severe undercutting. In AC welding, the angle of electrode does not have to be used to fight arc blow. It is used instead to control the depth of fusion and the contour of the weld, taking full advantage of the steady directional effect provided by the cupping action of the electrode coating. Uniform welds with proper contour and good fusion at the root of the joint are the result. Deep fillets, as the name implies, have deeper fusion than fillets made with normal technique. Deep fillets are made in either the flat or horizontal positions. The gauge size of the deep fillet and the amount of filler metal required to make it are smaller than in the normal fillet of equal strength. The all-important factor, whether in single pass fillets or in the first pass of multi-layer fillets, is uniformly deep fusion. In the deep fillet technique, the angle of electrode is vital. The electrode should be held at about this angle in the direction of travel, and at this angle with the plates. In order to secure uniform depth of fusion, the proper angle must be maintained throughout the length of the joint. The arc is struck, and the electrode rested lightly on the work while moving at a speed of travel which will maintain the desired fillet size. The type of electrode used for deep fillets develops a deep, uniform cup when AC is used. The cup automatically maintains the correct arc length when rested on the work. It directs the arc and protects the hot metal from contamination by the atmosphere. With DC, when severe arc blow is present, the cup on the end of the electrode may become distorted due to deflection of the arc. This destroys the usefulness of the cup in maintaining the correct arc length and in directing the arc properly. Troublesome arc blow may also make it necessary to change the angle of the electrode in order to control the molten pool, thus adding to the difficulty in producing uniform deep fusion. By eliminating arc blow, alternating current makes deep fillet welding easy and results in clean, uniform fillets right up to the end of the joint. Good welds in the vertical position are easily made with alternating current. The technique is just like that used in DC welding. The less whipping, the better. Since arc blow is not a problem in AC welding, full attention can be given to the control of the molten pool. Overhead welding with alternating current, like flat, horizontal, and vertical welding, is made easier in the tight places by the elimination of troubles due to magnetic arc blow. Note the good, uniform appearance of both the vertical and overhead welds. In flat position welding, much of the time and effort lost in frequent changes of electrode can be saved by using large diameter electrodes. With alternating current, 3/8-inch diameter electrode can be used with high currents to produce smooth, uniform welds. With direct current, the benefits of large electrodes are lost when severe magnetic blow is encountered. The difference between AC and DC welding is readily apparent when using 3/8-inch electrode in this flat fillet. Even with the smaller size of electrodes used in groove welding, this same effect is present in a DC weld. A radiograph of a weld made under this handicap is likely to show irregular fusion and inclusions in the weld metal. AC welding makes this kind of work easier by steadying the arc and simplifying the technique, because the operator does not have to fight arc blow. The result is a finished weld of which any welding operator can be proud, and which the X-ray proves is sound throughout.